Hi everyone. So today we're going to talk about freefall, and we're actually going to talk about kind of the simplest aspect of freefall. We'll get into more advanced situations later, but we're going to focus on freefall one-dimensionally. So we have only objects moving in straight lines. And our objective here is to apply kinetic equations to an object when it's in freefall, and we'll talk about what that means in a soon. And studying falling objects is quintessential when it comes to studying physics, so it's important that we do so. First, I'd like to answer this question here. So which will hit the ground first when dropped, a bowling ball or an apple? Hopefully by the end of this lesson you'll have a justification as to what the correct answer here is. Alright, so free fall is an important specific case of constant acceleration. So when we have an object moving only under the influence of gravity and no other forces, that's when an object is in free fall. Now, granted, we haven't studied forces yet, but basically whatever we're looking at is only under the influence of gravity it's in free fall. So a lot of times if you just imagine an object falling, it's going to be in free fall. That being said, when we imagine an object falling or moving through the air, a lot of times we think, oh, there's also air resistance, which would be another force acting on our object. Most of the time, we're going to be assuming that air resistance is negligible and can be ignored. So when I say negligible, what I mean is that the effect of air resistance is so small compared to the effect of gravity that we can just ignore it. All right. We won't always be able to do this, but most of the time this is going to be the case. So basically, if an object is moving solely in the air and not interacting with anything else, it's in free fall. So for example, a ball rolling on the floor, that is not in free fall because it's also interacting with the floor. The floor is acting on the ball as well, so it's not in free fall. Alright, so kind of moving on here. Galileo made some interesting observations when it comes to the idea of free fall. He noticed that if you drop two objects of different weights from the same height, ignoring air resistance, they're going to hit the ground at the same speed. Alright. Not only at the same speed, but also at the same time. So that's really interesting because that implies that any two objects in free fall, regardless of their mass, are going to have the same acceleration. So that's saying that free fall acceleration is the same for all objects, which is very interesting. Now we can see this experimentally actually. This was done on the moon, this experiment. You should be able to see this video, and actually we're not going to be able to hear it only because I don't have the kind of fancy video recording software to record computer audio. But here he's explaining that in his left hand to us is a hammer and his right hand is a falcon feather. And he is on the moon in this video. So he's going to drop both the hammer and the feather at the same time, and we should be able to see that they hit the floor of the moon at the same time. Alright. So let's see. And and bam. So both the hammer and the feather hit the ground at the same time. So that implies that the acceleration that they're experiencing in free fall is the same. Right. So this situation in particular was dropping objects, right? So we can observe a couple things when the objects dropped, right? We can observe that once the objects are no longer in contact with the hand, they are going to be in free fall. We also observed that they started from rest and that these objects moved downward. And as they move downward, they speed up as they move down. So from this, since the object is at rest and then speeds up in the downward direction, this implies that the acceleration associated with free fall is in the downward direction. So remember, whenever the velocity vector and acceleration vector point in the same direction, the object is speeding up. If they point in opposite directions, it's slowing down. So since our object's moving downward, the velocity is downward, and excuse me, and it's speeding up, therefore acceleration has to be downward as well. Now, just a little caveat here, when I say downward, what I mean more precisely is towards the center of the planet. Right? So, but I'm talking relative to whoever's dropping the object. So dropping an object is pretty kind of straightforward in terms of kind of picturing what's going on in terms of acceleration. But let's think about what happens when, rather than just dropping an object, let's throw an object upward, straight upward. So I want you to think here and take a pause. So if we throw a ball straight upwards, is it in free fall? Secondly, if the speed of the ball, what speed does the ball have at its peak when it's thrown straight upward? And is the ball accelerating at that peak location? All right, so here, 3 parts of this question. So first, is the ball in free fall? And the answer is yes, if it's released from, as long as we're analyzing the moment it's after it's been released from the hand. So it's solely under the effect of gravity on the way up and on the way back down before it hits the hand again. So once it's caught, it's no longer in free fall. We're only looking, so if we're just analyzing the motion after it leaves the hand, yes, it's in free fall, assuming we're ignoring air resistance, which is what we're doing. Secondly, what speed does the ball have at its peak when it's thrown straight upward, and is the ball accelerating at its peak? And actually I have a little bit more to say on the next slide about this. All right. So as the object leaves the hand and moves upward, right, as it's, I'm going to use the word falling upward, which kind of counterintuitive to usually what we think, but that's what we're dealing with here. Since the object moves upward, it's slowing down, right? It's slowing down before it hits its peak height, and then exactly at that peak height, it pauses for just a moment, and then, when I say just a moment, I mean literally a split moment, infinitesimally small moment in time. But then it turns its direction around, so to speak, and then starts falling downward and increases its speed back downward. So whenever you're throwing an object straight up and down, all right, straight up and down, its speed at the top is 0. All right, and we can just think about that. Just before it reaches the top, its velocity is upward, even though it's very small. Just after it reaches the top, it's now moving downward, even though that speed is very small. So if we're moving from, let's say, call upward positive, going from a positive direction to then a negative direction, it has to reach 0 speed. Now, what's interesting is that the acceleration points downward throughout the entirety of the motion, right? And when I say motion, I mean that 0 value as well. So as the object moves upwards, so since it's going up, it's moving up, its velocity is upward. So that vector is pointing up, but it's slowing down. So the acceleration points downward. So since they're pointing in opposite, since it's slowing down, acceleration has to point downward. All right, so now we see throwing an object upward, as it moves up, acceleration is also down. We reach that 0 point, still accelerating downward because we go from a 0 speed to then having a downward speed. So therefore it has to be accelerating at that moment. And then as we already talked about, acceleration is also pointing downward as the object moves downward because it's speeding up. So throughout the whole motion, we have this acceleration. And actually this acceleration is a constant value throughout its whole free fall motion. Right? It's really nice because we have a nice symmetry because of this, right? What kind of symmetry here am I talking about? And let's say, again, I'm still using this example of throwing a ball straight up and down, but when the ball leaves the hand, it leaves the hand with some sort of speed, right? It takes some amount of time to reach the peak height where it has 0 speed. It then falls back down. It takes the same amount of time to fall back down to reach the hand, assuming the hand hasn't moved. And then it reaches that same speed it left the hand with, right? So really we have this really nice symmetry because the acceleration is constant, and the symmetry we're going to use to our advantage in problem solving. So let's put some numbers to this, right? So near the surface of the Earth, this acceleration value, free fall acceleration, is 9.8 meters per second squared, and the direction of that is vertically downward. So because we use this number so often in physics, it's kind of ridiculous. We attribute a symbol to it to represent it, right? Because physicists are lazy. Rather than always writing 9.8 meters per second squared, we use the symbol lowercase g, not capital G. Capital G represents something else, right? So lowercase g. Now, something to be careful with. By definition, g is always positive. Acceleration, like that letter represented, is always a positive value. G is always equal to a positive 9.8 meters per second squared. Right. Now, if we're calling upward being positive, well, that acceleration is now then negative. So the way we represent that is putting a negative outside the letter G. So negative G is what we would write. Okay. So just be careful there. You're never plugging in a negative number for G. We always represent the negativity of that value separately. And what's really nice, so since the acceleration is constant, we can use kinematic equations with this value for acceleration to help us solve these types of problems in this type of situation. So if we have an object moving through the air with only gravity acting on it, we automatically know, all right, I know the magnitude of that acceleration is going to be 9.8 meters per second squared, assuming we're on Earth, right? So, just be careful. G is not called gravity. This is actually a huge pet peeve of mine, and I will come after you if you call G gravity. Gravity is a force, right? We'll talk about forces next unit, but forces are not accelerations. They are different things entirely. So when you're talking about G, you're talking about free fall acceleration, or you can say the acceleration due to gravity, right? Don't just say G is gravity. That's incorrect. Secondly, 9.8 meters per second squared is only accurate near the surface of the Earth, right? This does vary at different locations, even on Earth itself, but especially if we're on a different planet, this number could be something else entirely, right? So for example, if you're on the moon, which is not a planet but a moon, but effectively there's some same things. When you're on the surface of the moon, the acceleration to gravity is actually about 1/6 this value. And this is why when you have someone moving on the moon, they kind of jump around. They jump around slowly, and that's because this free fall acceleration is smaller. And let's see. So some connotations. Sometimes you'll represent an acceleration value in kind of, let's say, units of G's, or I should really say here, instead of units, factors of G. So if you say something has an acceleration of 1G, that means their acceleration is 9.8 meters per second squared. So if something has an acceleration of 20G, that's going to mean they have about twice 2G. Okay. And finally, we're pretty much always going to round to 10 meters per second squared. AP exam basically tells you to do this. So we're kind of imprecise here, but that's 100% okay, because the whole point of our physics class is the problem-solving aspect, not the fact that our answer is very is super accurate. All right. Okay, so finally, oh, here I have a different question. That should not say paper, but anyway, now you should be able to answer the question we started off with, which will hit the ground first. I think I said a bowling ball or an apple, so please replace this here with bowling ball or an apple and explain your reasoning.